In this section, we're going to learn how to find the domain of a function. Domain is just a fancy way of saying, okay, which x's am I allowed to use as inputs in my function? So there are a couple of ways that you can think about domain. So domain, sort of in the most simplistic way to think about, that's the x values. But which particular x values, that depends on the problem. Mainly you want to think about which x values we're allowed to use in a particular function. Another way to think about the domain is also to think about inputs. So what inputs we can use inside my function. So that's sort of some synonyms that you can think of when we are trying to look for the domain of a function. This example is giving us the function f of x, and it is x squared plus 2. Notice that this is a polynomial. Notice that there are no radicals involved. There are no denominators with x's involved, so there are no rational expressions. It's just a plain polynomial, something squared plus a number. What we want to find out is we want to find the domain of this function and then write it in both interval and set notations. Okay, so to find the domain, what we're really looking for is which x's am I allowed to plug into the function so that my resulting function is still a real valued function. Basically, another way to think about this is, are there any x's that I am not allowed to use in this function? Well, since this is just a polynomial, imagine entering negative numbers. Well, a negative number squared is a positive number, plus another positive number gives me another number, so that's not an issue. Can I plug in positive numbers? Of course. Can I plug in 0 as well? Yes. Can I plug in fractions? Yes. Can I plug in full numbers, integers, whole numbers? I can actually plug in any number that I want, that I can think of, right? Any real number that I can think of. And there's not going to be any issues at all with this function. I'm not going to get any undefined. I'm not going to get any imaginary numbers because there's no way for that to happen. So in that case, because there are no problematic x's, there are no x's that are going to cause me trouble, that means that I can use any number, any real number whatsoever to input into this function. So that means that the answer for this kind of a expression, this kind of a function that's really just a polynomial, the answer for the domain is all real numbers, because there are no real numbers that are going to be problematic for us to input into this function. And we need to show that in two ways. We need to write that in set notation. So just to write that in set notation, we're going to look at all those numbers x such that x is a real number. And then to write it in interval notation, we write negative infinity to infinity to show all real numbers. We have a function f that varies with respect to the variable t. So we have the same question, which inputs t can I use? Or equivalently, are there any values for t that I'm not allowed to use? Well, something that we notice is that I notice a fraction, right? This is a rational function, and I have a variable in the denominator. Now, what we know from previous material is that we cannot possibly divide by 0. So I can probably use any positive number that I want for t, right? Because that's just going to be a fraction over here. I can also use any negative number for t, because then I'm going to get a negative fraction. But can I possibly have t equals to 0? That would be really problematic, because remember, anytime that I try to divide by 0, right, so 1 divided by 0, that's undefined. That's problematic. That's problematic. So that means that I can use any value for t that I can think of, any real value for t that I can think of, except for 0. Because as soon as I make t equals to 0, I'm going to have an undefined result. So what does that mean? That means that the domain is everything except for t. Well, how do we write that in set notation? In set notation, that means I'm going to look for all those values x, or I'm allowed to use all those values x, except for x equal, or sorry, in this case it's not x, it's t, right? Because our variable is t, not x. So I'm allowed to use all those variables t, and then with one single condition, right? That t cannot be equal to 0, because as soon as I make this t equals to 0, I'm going to divide by 0, and I cannot have that. And then what about an interval notation? In interval notation, how do we write everything except for 0? Well, that means I'm going to take all the numbers smaller than 0 all the way to 0. I am not going to include 0, but then I'm going to take everything from 0 and above. So that gives me all the numbers except for 0, because remember, parenthesis means I'm not including that particular number. This is a very similar example in the sense that we have a rational function, right, with the possibility of the denominator becoming 0, because we have a variable in the denominator. So it's possible maybe that it might become 0 at some point, but we want to avoid that. So anytime that you see a rational function, right, and you don't see it combined with maybe a radical as well, but just a plain rational function where you've got a variable in the denominator, the easiest way to find the domain is to set the denominator equal to 0. So set denominator equal to 0. That's going to give you any problematic numbers that you might have that you don't want to include in your domain. So in this case, my denominator is x minus 3, and I'm setting it equal to 0. This gives me x equals to 3. That gives me the problematic x that I do not want to include in my domain. And why is it that I don't want to include it? Because if I choose x equals to 3, then what's going to happen? 3 minus 3 is 0. I'm going to get a 0 in the denominator, and I'm going to get an undefined. So this number over here that I just solved for, that's the problematic x that I do not want to include. So then how do we write the domain? In set notation, this is going to be, or we don't need the equal. In set notation, this is going to be all those values x, and then we have one single condition, that x cannot be equal to 3, because if it is, we're in trouble. We're going to be dividing by 0. To write that in interval notation, how do we write everything except for 3? Well, everything except for 3, that means everything below 3, not including 3, and then everything above 3, and we are done. In this example, again, we see a rational function and some variables in the denominator. So there is a possibility that we might at some point divide by 0. So let's find those problematic x's that are going to make us divide by 0 so that we do not include them in the domain, so that we can avoid them. Well, how do we do that? Anytime you have a rational function and you don't have a radical involved, then you set the denominator equal to 0. So we're going to have x squared plus 4x minus 5 equals to 0. This can be factored into x plus 5, x minus 1. Setting each one equal to 0, we get x equals to negative 5 and x equals to a positive 1. These x's that we just solved for, these are problematic x's. They're problematic in the sense that if I choose to use any of these x's into my function, I'm going to be forced to divide by 0, which I don't want. So I want to avoid these numbers. I don't want them in my domain. So then how do I write the answer then? Well, the set notation is going to be, okay, I want all of the x's with two conditions. The x cannot be negative 5, and the x cannot be 1, because I want to avoid those numbers completely. Now, how do I write this in interval notation? Well, let's think about it graphically. So here's my negative infinity and positive infinity. Here is my negative 5 and 1. Well, I want to use everything except for these numbers. I don't want negative 5 and I don't want 1. But I do want to use everything else, because all the other numbers don't give me trouble, right? They're not going to force me to divide by 0. But these two particular numbers, negative 5 and 1, they are going to force me to divide by 0. So I want everything that's highlighted except for these empty circles, negative 5 and 1. So then how do we write that in interval notation? Well, I want everything below negative 5. I want everything between negative 5 and 1. And then I want everything above 1, just not to include the actual numbers negative 5 and 1. If you have an even root function, so in this case this is a square root, what we want to avoid is a negative under the root, because we don't want to have imaginary numbers. So we want a real valued function. So we want to keep whatever's underneath the radical to be positive. So that restricts us as to what kind of inputs we can have. So what m's am I not allowed to use? Well, I cannot use the m's that are going to make the entirety of my root negative. So for example, as soon as I make this m to be the number, let's say, less than 2, that's going to be a problem, right? So, for example, imagine that this m is the number 1. 1 minus 2 is -1, and square root of -1 is not a real number. So I don't want my m to be a value that's going to force me to start involving imaginary numbers. So the easiest way to be able to calculate what m's we are allowed to use is anytime that you have a radical equation, take whatever's underneath the radical, so anything that's underneath the radical, and so take that, so in this case it's m minus 2, and set it as greater or equal to 0. And the reason why we want to do that is because we want what's under the radical to be either positive or 0. We just don't want it to be negative. So then once we set this up, then to solve it, we just add 2 to both sides, so we get m is greater or equal to 2. This gives me the domain of my function. So there are 2 ways to write that. In set notation, this is going to look like, okay, I can use all those variables m such that m has to be greater or equal to 2, so that's the condition. Or in interval notation, that's going to be bracket 2 comma infinity, because I want to use everything that is above 2, but also the actual number 2. That's why we use the bracket. This is an interesting case because it combines both a rational expression with a radical together. So normally, if this were just a rational expression, we would set the denominator equal to 0 and find the problematic x's. If this were just a radical equation, we would take what's under the radical and set it as greater or equal to 0. But I have both in this case, so we got to be a little bit careful. Let's tackle first the radical. Normally, if I would just look for the domain of the radical, I would take whatever's underneath the radical, so whatever's underneath the radical, and set it as greater or equal to 0, right, to find the domain. But what's the problem? The problem is that if I set this to be equal to 0, well, square root of 0 is going to be 0. But can I possibly have 0 in the denominator? I cannot. So that tells me that I can only set, so I cannot possibly do this, right? I can only do x minus 2 is greater than 0. That's the only thing that I can do. I cannot possibly make it equal to 0 because then I would have to divide by 0. And we don't want to do that. It's going to be undefined. So in that case, we eliminate that second part about equaling it to 0 and only keep it as greater than. So then to solve from here, we get x is greater than 2. And then to write it in set notation, we've got all those x's such that they are strictly greater than 2. And in interval notation, that is 2 to infinity. So basically everything that's above 2, but not including 2, hence the parenthesis. We have another rational function here. So we know how to find the domain. We set the denominator equal to 0. So x squared plus 4 equals to 0. And then we solve. So we get x squared equals to -4. Taking the square root of both sides. Don't forget the plus and minus. We get x equals to plus and minus 2i. But then what is the domain? Well, the domain looks at what x's am I allowed to use so that my function is a real valued function. To set the denominator equal to 0, that means I'm looking for any problematic x's. So I was looking for any problematic x's, but the only problematic values that I found are not even real numbers. They're imaginary numbers. So then what does that mean? Can I possibly have any numbers x that are going to force me to divide by 0? That's not possible because there are no real numbers that are going to give me trouble. Only imaginary numbers, but we don't even care about them. So in this case, the only problematic numbers are imaginary. That means there are no real numbers that are problematic. So in terms of the domain, that means that the domain is all real numbers. So in set notation, that's all the x's such that x is a real number. And in interval notation, it's -infinity to infinity. So we said that the domain represents all the x values or all the inputs. The range means all the y values or all the outputs. So another way for us to look at a function instead of seeing f of x equals to something, another way of seeing a function is by looking at a set of points. So these are just a set of points. How many of them do we have? 1, 2, 3, 4 points. So this is a coordinate. This is the x, y, and so on. So when x is 0, y is 1. When x is 3, y is 4. For x equals to -5, the y that belongs to that is 7. When the input is -1, the output is -13. So that's how we can think about this set of points. So what the problem is asking us is to find the domain of this function, and the domain is literally all the x values. So 0, 3, -5, and -1. So all the inputs of the function. The range are all the y values, or all the outputs that correspond to the inputs that we had. So then the domain would be, let's see, so domain are all the x values, and that's 0, 3, -5, and -1. And the range is composed of all the y values, or all the y outputs, 1, 4, 7, and -13. Done.